Hello everyone and welcome. My name is Jason Gregerson. In this video, we're going to be discussing numerical integration. We're going to have two main goals. First, we're going to discuss why use a numerical technique, and after that, we're going to program a specific method, the left sum approximation. First, why? Why use a numerical integration technique instead of just evaluating a definite integral using an antiderivative? There's three main reasons. First, there might not be an antiderivative. Not all integrands have a closed form antiderivative. So here's an example of a complicated looking function, 3e to the cosine of 2x squared plus the natural log of sine squared plus 2. And if I try to evaluate this using the integrate command in Mathematica, it's just going to return the actual integral. It says I don't know how to do this because I can't find an antiderivative. However, if I use the nintegrate command, telling Mathematica to use a numerical technique to evaluate the definite integral, it'll return a value no problem. So if I don't have an antiderivative, I'll need to use a numerical technique. The next reason that's cited in the text is data. Often in real life, our information is given to us in terms of a data set, not a function. So here's an example of a data set. If I need to integrate this to calculate some value, I would have to use a numerical technique. And the last reason is because of time. And this was often not discussed, but it might take a computer program a lot less time to approximate an integral numerically than to use an analytic technique. For example, I have another function down here, and if I evaluate this cell and tell Mathematica to calculate the actual value of the integral, and I've wrapped the timing command around this, so here is the value of the integral of my function from 1 to 2, and here is the time it took to generate that value. So it took Mathematica about 2.7 seconds to calculate this integral. Now I'm going to copy this line of code and paste it down below, and now we'll see how long it takes for Mathematica to generate a value numerically. So here I'm getting the numerical value. You can see here it took 0.01 seconds. Now if I put my cursor after these guys to see more digits of precision, we can see that right about here my values do start to differentiate. So it looks like my values are good to about 9 decimal places, but it took Mathematica 2.7 seconds to calculate the exact value, but only 0.01 seconds to get the approximation good to 9 decimal places. Now that might not seem like a long time to you, but in a real life problem, for an advanced method, I might have to integrate something 10,000 times, or integrate a function over 10,000 different intervals, and so that 2.7 seconds can certainly add up. Alright, so now we know the why. Now let's see if we can actually write a program to do numerical integration. Alright, so we developed our definition for the definite integral through the idea of finding the area under the curve. And so we're going to do the same thing when it comes to numerical integration. We're going to set up a system here to do the left sum approximation. So we'll start by looking at our function. We're trying to find the area under this function, 1/2 x minus 2 quantity cubed plus 5, on a specific interval. In this case, we'll look at the interval from a equals 1 to b equals 3. And so the way we kind of defined our definite integral was that we would take our interval from 1 to 3, break it up into some subintervals, where each of the endpoints was x0, x1, all the way out to xn, or x4 in this case, where I have 4 intervals. And once we have our intervals, we would create rectangles above each interval. And then we would calculate the area of each rectangle by evaluating the function at the endpoints, using that as the height of the rectangles, and then calculating the base of each rectangle, adding that guys up. And that would be an approximation to the area of the curve. And if we increase the number of intervals, we'd get a better approximation. And so we defined our definite integral as the limit as n goes to infinity of that sum. For numerical technique, we're just going to avoid the limit. We're actually going to calculate the area of a finite number of rectangles and add it up. So how do we actually calculate these areas and add them up? Well, first we got to enter in the information we know. So I've already defined my function, and then I have to enter my other information. So here's my function. I know I'm integrating it from a equals 1 to b equals 3, and I've decided to use n equals 4 subintervals. Once I have that information, I can actually calculate the base of each of the rectangles, the delta x in this case. In Mathematica, I'm going to call mine dx because it's a little easier to typeset than the delta x, and that's going to be the interval width, which is 3 minus 1 in this case, or more generally, b minus a. And I'm going to divide that by the number of intervals. In this case, that would be 4, but more generally, it would be n. And then once I put some of this code in Mathematica, I want to make sure I'm running the cells. And that way I can actually see and confirm the values I'm getting. In this case, I have a delta x value of 1/2. That makes sense according to my picture. So now I have my delta x. The next thing I have to do is figure out what the x sub 0, the x sub 1, the x sub 2 values are. So if I'm thinking about what those values are, the x sub 0 would just be my a value. It's the left side of my interval. Now the x sub 1 value, I'd have to start at my left-hand side and add delta x. So my x1 would be a plus 1 times delta x. To get to x2, I'd have to add another delta x. In other words, that would be a plus 2 times delta x. X sub 3 would be a plus 3 delta x. So what I can see that in general, the x sub I endpoint would be a plus I times dx. Now once I have a general formula for the x sub I value, I can then use the table command and create a list of these values as I goes from 0 to n. And I really encourage you to use the table command to generate the points, because then you can actually check your work and make sure that it's getting the right points that you expect. So here these values do line up with my picture. They do look like x0 through x4. Now if I want to calculate the areas, I need to evaluate the function at these endpoints. But I actually don't use that x sub 4 value. What I can see is in that last rectangle, the height is the f of x sub 3 times the base of delta x. So when I'm using the left sum technique, I don't actually use the far right endpoint, which means I can generate my values from I equals 0 to n minus 1. And once again, I can run that to really confirm that I have the points that I'd like to use. Now what do I want to do? I want to calculate the height of these points. So I evaluate all of these points, my function at all these points. These should be the associated heights of the rectangles. What do I do with those heights? I multiply them by the base of each of those rectangles. So this should be the area of each of the sub-rectangles. And lastly, I want to add all these values up, and to do that, all I do is change the table command to the sum command, which adds them all up. And so now my first approximation to the area under this curve. Now one thing I noticed, I'm getting a value of 39 over 4. I kind of like to see the decimal value. That'll give me maybe a better sense of what the actual area is, but not only because of that reason, but also because if Mathematica is trying to calculate the exact values using fractions as opposed to using floating point values, it can actually make the algorithm go a lot slower. So you should always put in a floating point value so you get a floating point value out. So 9.75. Now that I have my code written and everything working, well, now I can just modify things. So now if I had a different function, let's say I wanted to integrate x cubed from a equals 0 to 1, and I wanted to use 400 intervals. Now I could just modify those values and run the cell, and I get some new value. Once again, decimal in to get a decimal value out. All right, so now I've done my first programming of the left sum technique. Now something else I might want to do with this program, though, instead of having to modify each of those little bits and rerun the whole cell, is I might want to package all of this into one big function definition. So that's what I'm going to do next. I'm going to package the program into a callable function. What does that mean? Well, here's the main piece of my code. So I'm going to copy that guy and paste it below. What I'd like to do is define a function. I'm going to call mine left sum, L sum. And I have some inputs, and then I'm going to use a colon equal to define this. So I got to make sure you use colon equal, not just equal. And then I have to define what the inputs to my function are. I want to plug in what the function is, the function name that I want to integrate. I'm also going to have to tell it over what interval that I'm integrating it over. And lastly, I want to tell it how many steps I'm going to use to generate my approximate value. So in this way, if I define my function, I can then just call left sum and put in my input values, and it will generate the left sum approximation. Now, one thing to be careful about here is that in my program as I've written it, I have these dx's here, my delta x's. But those delta x's really change as b and a and n change. So if I plug my values into my command below, it might not be updating my dx properly. So what I have to do is I have to take what dx is equal to in terms of b and a and n and just paste that down into this new program. So I'm going to replace all my dx's with that expression for dx. Now my whole program is really in terms of my function a, b, and n. So I'm going to hit Shift Enter to evaluate this. Now I have defined the left sum program, and now I just need to call it. So to use my function, I would just define something. So here I'm defining what function I'm going to use. Maybe it's x to the third power like we did before. So I've defined a function, and I will call my program and say I want to look at the left sum approximation for the function g, where I'm integrating from 0 to 1, and I'm going to use 400 steps. And I can just kick out some value. Once again, decimal in to get a decimal out. And here I could just modify to get different values depending on my different inputs. So now I've packaged up my program nicely. Now the one last thing I'm going to show here, now that I've already packaged up my program, is I want to compare it now. What we saw earlier was that we had this function time that we defined, where it took a long time to integrate analytically, 2.8 seconds, as I ran it a second time down here. And I have an n integral time as well. So let's rerun this one more time. I might get some slightly different values here. So I want to compare how my function would do. So I'm going to call left sum. I'm going to pass in the function name of time. I don't need the of x here. I can just put in the name of the function. And I'm going to integrate it from 1 to 2 with a decimal in this time. And I'm going to say use 4,000 steps. And we're going to run this thing. And I also want to wrap a timing command around this to see how long it takes my code to run. And so what do I have here? Well, so far it doesn't look like my value is very accurate. I'm not even good to one decimal place. So I might have to use more steps. So let's crank this up a little bit to use 10,000 steps. Play with it there. Not quite yet. How about 100,000 steps? Okay, so now I'm accurate at 2 decimal places, but my time is starting to creep up here. So now I'm at 0.7 already. So what I can see is that my value is pretty accurate to do decimal places, and it's already going much faster than the integrate command. That being said, my code is taking much longer than Mathematica's integrate, and my value isn't as good. And of course, the reason for that is we're using left sum technique, but Mathematica has built-in techniques that are much more advanced at left sum. So far we've practiced programming left sum, and you'll be able to practice some other techniques and a little bit better techniques as you go through the rest of this course. All right, that concludes this video. Thanks for watching.